Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is a multivariate time series analysis with a focus on specific data examples. In this lesson, I will continue with another data example referring to the prediction of a river flow. In this study, we'll forecast the flow of the Chattahoochee River, which is part of an important hydrological system in southeast of the United States. The Chattahoochee River originates in the Blue Ridge Mountains of the Appalachian Highlands in northeast Georgia and flows southeasterly for 120 miles and then towards south along the Georgia-Alabama border for about 200 miles. The Upper Chattahoochee River watershed is the most important, if not unique, source of water supply for Atlanta area. It also plays a key role in shaping the whole basin hydrological and ecological system from which it belongs. Our understanding of such environmental systems can be substantially improved by using multivariate time series analysis and modeling techniques. The main hydroclimatic time series, namely precipitation, ground air temperature, and stream flow, are used in this study, where the primary objective is to forecast the stream flow. For this study, temperature and rainfall data was acquired from the National Weather Service Forecast Office, and the river flow measured by the discharge in cubic feet per second for the downstream site of Beaufort Dam was acquired from the U.S. Geological Survey Water Resources Database. The data available from the two sources have different time frames: 1956 to 2017 for river flow and 1950 to 2017 for temperature and rainfall. Thus, we will need to first process the data to model all three time series within the same time frame. We first read the data from three different files with somewhat different structures. Make sure to open the files to learn about the structure of the three data files. First, we're missing data from one observation in rainfall for October 1964, which will replace it with the average of the neighboring observations, the average between September and November. Next, we remove the first 6 years from the temperature and rainfall data. We'll also have data until July 2017 for temperature and rainfall, but only until March 2017. Thus, I remove the last four values in the temperature and rainfall time series also. Next, I convert the vectors of observations into time series using the TSR command, specifying frequency equal to 12, since the data are observed monthly. Last, I plotted the time series and their auto and cross correlation plots. These are the time series plots for the three time series. The temperature time series clearly shows seasonality. The seasonal changes in rainfall are not significant, even though there are visibly higher amounts of rainfall during winter months. More importantly, the relationship of temperature and rainfall to the river flow is the one that we're interested. The air temperature shows that the potential evapotranspiration during summer months is nearly 4 times higher than that during winter months. Thus, stream flow time series exhibits seasonal patterns related to these variations. During winter months, when the potential evapotranspiration is lowest in the year, the stream flows are mainly determined by the precipitation. While during summer months, when the potential evapotranspiration is higher than the amount of water falling within the watershed, the stream flows are consistently low despite of the variations of precipitation. The ACF plots show the high degree of seasonality for temperature, and the ACF plot for rainfall shows large values at the lags 1 and 12. However, there is not a significant lead-lag relationship between river flow and the two time series as shown by the cross-correlation plots. Next, we're testing the hypothesis of stationarity for all the three time series. Here I'm applying the R command adf.test test, and where the input is river.ts or any of the time series, any of the 3 time series. Note that I also specify here alternative equal to the stationarity. And this means that the alternative in this hypothesis testing procedure is that the time series is stationary. We see that from this test that the p-values are all small, indicating that we reject the null hypothesis, or that the alternative hypothesis of stationarity is not rejected. Hence, we have stationarity. But if we consider differencing the time series, the order selected for differencing the time series is 0 for all 3 time series. While for the river flow time series this may be the case, we have learned from previous plots that a difference of order 12 may be appropriate for seasonality in the temperature and the cyclical pattern for rainfall. The reason why the ndifr command does not identify an order 12 difference is because it only considers lower order differences. Next, I consider a log transformation of the time series. This is primarily because the variability in the river flow time series varies with time, suggesting heteroscedasticity or non-constant variance. One approach to deal with this is using a transformation. For example, here we're using the log transformation. Last, in order to account for the seasonality in the temperature and cyclical pattern in the rainfall, I applied the order 12 difference for all 3 time series. These are the log transform time series. The non-constant variance for the river flow time series is stabilized. These are the plots of the difference in time series. The seasonality is in the temperature and cyclical pattern in the rainfall are not present anymore. This is also evident from the ACF plots. We see some cyclical pattern left in the rainfall, indicating that removing the seasonality is not sufficient to account for the cyclical pattern. In summary, in this lesson, I introduced yet another data example that I will use for illustrating multivariate time series analysis. In this lesson, I provided an exploratory data analysis for this example. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on multivariate time series analysis with a focus on data examples. And in this lesson, I will continue the example of prediction of river flow, but this time we'll focus on modeling using univariate time series approaches. Again, in this study, we'll forecast the flow of the Chattahoochee River, which is part of the important hydrological system in southeast of the United States. And this is the upper Chattahoochee River watershed is the most important, if not unique, source of water supply for Atlanta area. I'll begin with the modeling of the river flow using univariate time series models. We'll apply the modeling on the log transform time series. I also split the data into training and testing, where the training data include all the years from 1956 until 2006, and the testing data include year 2006 and the first 3 months of year 2017. I'm not showing you here the code for model selection since it has already been discussed for other case studies in previous lessons. The selected order for the river flow time series 1 and 4, AR equal to, the AR order is equal to 1 and MA order is equal to 4. With no differencing identified, that means D is equal to 0, and the difference order for the seasonal component is selected to be equal to 2. With these selected orders, we fit the seasonal ARIMA model as provided on the slide. These are the residual plots for the fitted seasonal ARIMA model. The residuals versus time plot does not show any particular pattern. However, the ACF plot points to large autocorrelations at lags 1 and 12. The histogram and the probability normal plot show that the residuals have an approximate normal distribution. From these plots, the only possible concern is that there is some autocorrelation in the residuals. Let's then apply a test for uncorrelated data using the box test R command. Two important units in this R command are fit df and lag. The input for FIT-DF is the number of coefficients in the ARMA model, and this is used because we are applying the box test or for the uncorrelated data on the residuals. Since we use an ARMA model with order 1 and 4, the FIT-DF is equal to 5. The lag input will need to be higher than FIT-DF. Here we consider it to be 6. We also have the option to use different test statistics provided by the type. The p-value for the testing procedure for uncorrelated data is large, which means that we do not reject the null hypothesis of uncorrelated residuals. Hence, it's plausible that the residuals are uncorrelated. The forecast R function in the library forecast can be used to derive the predictions for the river flow time series based on the seasonal ARIMA model. To plot the forecast, we can apply the forecast function with input the fitted model and the number of lags ahead for prediction, in this case h equal to 15. Then we can apply the plot function to the forecast object. The plot is provided here. The black line shows the observed time series, and at the end we have the predictions along with the prediction intervals. While it's hard to assess how close the forecasts are to the observed time series values for the test data, we can see that the predictions have high uncertainty since the prediction intervals are wide. Next, we'll extend the ARIMA model to account for exogenous factors such as temperature and rainfall. Just like the VAR-X model, this is called ARIMA-X. The ARIMA-R command allows specification of exogenous factors through the XREG option. As provided here, both the temperature and rainfall time series are considered exogenous factors in modeling and predicting river flow. We apply again the model selection. This time, the selected order for ARMA are 1 and 4, whereas for seasonality is 0, indicating no differencing for the seasonal component when accounting for the exogenous factors. Next, I fitted a model and plotted the residuals. The residuals are here. The residual plot versus time does not present any pattern. The ACF plot of the residuals resembles that of white noise, indicating plausibly uncorrelated residuals. The residuals also have an approximate symmetric distribution and approximate normal distribution as provided by the histogram and the probability normal plot. Here we apply once more the test for uncorrelated data. Similarly to the ARIMA model without exogenous factors, we do not reject the null hypothesis for uncorrelated residuals when applying this testing procedure because the p-values are large. We can obtain the forecast similar for this model, for our ARIMA-X model, similar as before. The R code used for extracting the point forecast and the lower and upper predictions intervals are in the R code files for accompanying this lecture. On this slide, I'm comparing the predictions using the ARIMA without exogenous factors in the upper figure and with exogenous factors in the lower figure. I specify the same scale for both plots for comparison. The prediction using ARIMA without exogenous factors are not better than when accounting for exogenous factors. The point predictions for ARIMA-X do not have as high uncertainty as when using the simpler ARIMA model. In summary, in this lesson, I provided the univariate modeling for the river flow data example. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is a multivariate time series analysis with a focus on data examples using the R statistical software. And in this last lesson, I will finalize the analysis on river flow data with an analysis using multivariate time series modeling. In this study, we'll forecast again the flow of the Chattahoochee River. We'll begin with a classic VAR model applied to the trivariate time series, including log transformation of river flow, temperature, and rainfall. As before, we first select the order for the VAR model, which is p equal to 1 for this data. When fitting the VAR model, we consider a seasonal deterministic component specified as season equal to 12, and we assume a trend specified as type equal to both, which means fitting both a constant and a linear trend. We can also further reduce the model using the VAR restrict R command. We'll next look at the outputs for the river flow for both the VAR and VAR restrict. This is the output from the VAR model for modeling the river flow time series. The first three rows in the output matrix of the estimates are for the coefficients for the lag t-1 time series. The next coefficients are for the constant and for the trend. And the last 11 coefficients are for modeling seasonality. Note that we only have 11 coefficients for seasonality while we are modeling monthly seasonality, and hence we should instead have 12 coefficients. Similar to modeling seasonality using dummy variables as introduced in the first lecture of this class, we only include 11 of the 12 dummy variables because the dummy variables are linearly dependent, and since we with the column of ones, and since we include a constant or the intercept, we only include 11 of the dummy variables. What can we learn from this output? First, the coefficients for lagged river flow and rain are statistically significant. Second, the coefficient corresponding to trend is not statistically significant, given that all other factors, modeling seasonality and zero correlation, are included in the model. Among the seasonality dummy variables, some of the coefficients are statistically significant, some are not. The R-square of the model is about 0.57, or if we would use interpretation from linear regression analysis, 57% of the variability in the response is explained by the predicting variable included in the model. This is the output from the restricted VAR model for modeling river flow time series. To note that the restricted VAR simply drops those coefficients which are not statistically significant, which is not the correct approach to do model selection, since as we learn in regression analysis, when removing one predicting variable, the statistical significance can be very different from the model including the predicting variable. To understand this concept, I recommend learning about variable selection from the online regression analysis course. Based on this output, we can see that the R-square has increased significantly to 90%. This is much higher than the full model. Does the temperature and rainfall grandeur cause river flow? Here is the output performing the wall test for the null hypothesis that all coefficients corresponding to the lag t-1 of the two-time series are 0. Based on this test, the p-value is small, hence we reject the null hypothesis. This test says that at least one of the time series grandeur causes river flow. Let's compare the predictions based on the VAR and restricted VAR models versus the observed time series for 2016 and the first 3 months of 2017, hence predicting 15 lags ahead. This time, I'm using the predict R command instead of forecast R command to show you a different implementation of the prediction. First, we consider the predictions only for the river flow, hence the $sign followed by the name of the time series. To know that the predict will provide predictions for each of the 3 time series, but we are only interested in the predictions of the river flow. Also note that the output of the predicted R command is a list, and only the first element in the list provides the predictions. The object called pred in this slide provides not only point predictions or forecasts, but also the prediction intervals for the predictions. We apply this implementation for both models. Here are the predictions and the prediction intervals. The points in red and green are the point predictions from the 2 models, and the dotted lines in red and blue are the prediction bands. Both models perform similarly. The point predictions are quite different from the observed data. More importantly, the observed data fall outside of the prediction interval. In fact, they underpredict and pointing to poor prediction overall. Next, I will illustrate the implementation of the VAR-X model, in which I fit a VAR model to the bivariate time series, including log transformation of the river flow and rainfall, while temperature is now an exogenous factor. This implementation is used only to illustrate the VAR-X model. The implementation using the VAR-R command with similar input as before, except that this time I'm including another option in the VAR function specifying the exogen equal to temperature. The rest of the implementation is just like the VAR model without exogenous variables. This is the output of the VAR-X model which now includes temperature as an exogenous variable. The regression coefficient for temperature as an exogenous variable is not statistically significant, given that we accounted for seasonality, trend, and zero correlation in the river flow modeling. Importantly, the estimated coefficients based on this model are similar to those from the model where temperature is an endogenous variable. In this slide, I'm comparing the prediction of log river flow based on the three models: VAR, ARIMA, and ARIMA-X. ARIMA-X and VAR perform similarly because ARIMA-X accounts for lag relationships at temperature and rainfall. ARIMA does not predict worse than VAR or ARIMA-X, but it does have more uncertainty, where the prediction band includes the observed values and hence better predictions. In summary, I concluded the analysis on river flow data with the modeling using multivariate time series, and I compared the forecasts based on univariate and multivariate time series models. Thank you.